gravity. And this m is the mass of this water. Okay? Now, because I'm looking at static fluid, the center of mass of this system is not moving. It has zero velocity, so that it has zero acceleration. Therefore, all this total force should cancel each other. Let's take up as positive. F water should cancel F air and gravity. So I'm just going to write it as equal. The combination of force from air and gravity will cancel the force from water, so it's not flying up. The force from water is canceling gravity, and force from air, so it's not going down, it's staying here. Okay? Now, the pressure of the air at here, let's call it P air, and let's call the pressure of the water here P water. So, if we look at this equation, the force caused by fluid will be the pressure of it times the area that is pushing. So the force from water will be the pressure of the water times this area, and the force from air will be the pressure of air times that area. Gravity is gravity. Okay? Now, what I'm interested in is the quantity pressure, because we just learned it, it's fancy. We want to know more about it. So what I want to know is the difference between the pressure up here in the air and down here in the water. So let's combine the two pressure terms into P air. There's still area minus P water, and it has the same area. So I am moving P water to the other side. Now don't do that. Let's move air to the other side. So this is water, this is air, and that should be equal to mg. So now I'm going to take the area of the parentheses. So now I have the difference between the pressure times the area. Again, I'm interested in how the pressure change at different locations. So I just want P water minus P air. What do I do with A? I move it to the other side, or I divide both sides by A. So I get the difference between the pressure is gravity divided by the area. Let me write this as delta P because it's a difference. But now, I'm not taking the difference between two time instants. When we talk about velocity, we are taking the difference of the position at two different times. But now, I'm looking at the pressure up here and down here at the same time. This difference stands for different location. I'm looking at the pressure of different location at the same time. This delta is the difference in location. Okay? So the pressure difference will be mgA. I'm going to do a trick. I'm going to multiply by this depth d. This is the amount, this is the height of the cylinder that I choose to be my system. I'm going to multiply by d, but if I do that, I need to divide it by d. Okay? Why do I do that? Because this area times this distance d will be something about the cylinder. What will be this area times d? What of the cylinder will be A times d?
Volume.
Good, Daisy. Indeed, the volume of the cylinder will be A times d. The reason I get d involved is because I want the volume. And I can write it as mass divided by volume times g and the depth of the cylinder I choose. What is mass divided by volume? Have you guys learned density before? So the mass of this water and this water is different because there are more water in this bucket. But they are both water. I want something that describes the fact they are both water. So what about these two buckets of water is the same? The ratio between the mass and the volume is the same. And we call that density, rho. Density is the amount of mass per volume. If I increase the volume of this water, I will increase the mass of this bucket of water. The mass of that bucket of water will be proportional to the size, which is the volume of it, and multiplied by the density, which is the property of water. You can have a bucket of oil and a cup of water and say, my bucket of oil is heavier than the cup of water. But we know that oil will flow on top of water. So what exactly is smaller about oil? Density. When you compare the amount of oil and water with equal volume, it will be more massive. The water will have more mass when they have equal volume. Or when you compare it in a fair game, which you just compare the ratio between the mass and volume, oil will have smaller density and water is bigger in density. Okay? So now, brought back in here, we finally arrive that the change of pressure will be the density of the liquid times gravitational acceleration and how deep you go down. This delta B, so it doesn't really matter which one you are subtracting, because now you know the pressure at deeper water is going to be bigger. So when you use this equation in here, all you know is that the water down here must have bigger pressure because it's deeper. And you're just going to write the pressure of the water will be bigger than the pressure of the air by rho GD. Okay? So the way you use this equation is to find out the depth between 2 points. And the pressure difference between these 2 points is going to be rho GD. Which one should be bigger? The deeper one. So you just write it like this. Okay? So far so good? So you can think of, so when you look at how I get it, when I have bigger D, when I go deeper, it's like there's more water on top of me. This pressure is providing a force going up, so the thing pressed down can be cancelled. When you go deeper into the water, there's more water on top of you and they are pushing you down. So the deeper you go, more water on top of you going down and bigger pressure. There's more water on top of you trying to press you when you go deep into the water, and that's why the pressure will increase. And exactly, it will be increased by rho GD. Rho is the density of water, G is gravity, D is how deep you go down. Okay? So we said this air is pushing the can right now. And if you measure the pressure, the amount of pressure here in Earth is about 101325 Pascal. And we call that 1 atmosphere pressure, 1 atm. 1 atm is just an easy way to tell you how big the pressure is than here. But we just learned that different heights should have different pressure. So the pressure down here around my feet and the air pressure on top of here around my head should be different. Let's try to use that formula and see exactly how big the difference is. For air, the density, you need to use the density of air. I want the pressure difference on top of here and down there. And here is air, so you need to use the density of air. G, and let's say my height is about 2 meters. That's a lie, by 2 meters low. This is 9.8. The density of air is 1.2 kilogram per meter cube. 1.2 kilogram meter cube. Let me show you how it compares to water. The density of water is 1,000 kilogram per meter cube. So you see the air is a lot lighter in terms of density compared to water, which makes sense. And it's 1.2 kilogram per meter cube of density. This is meter per second square times, let's say I am 2 meters tall. Let's say this is 1, 10, 2, so it's about 20 Pascal. If you use kilogram meter per second, you will get Pascal. 20 Pascal compared to 101325 Pascal is a negligible difference. The pressure down here is 1 atm. The pressure up here is 20 Pascal, smaller than 1 atm, but if you subtract it, it's still about 1 atm. So usually, when we are looking at this floating ping pong ball, the pressure of air around the surface of the water and the pressure of air on top of the ping pong ball, we'll say it's just the same. The difference is not that important. The force from the air can be computed just by this air pressure because that's how big it is. And if you want to if you take into account the difference, it doesn't really matter. Okay?